Today we will finish link state routing. The test tomorrow will cover everything we've seen today and the previous weeks. And the lab will continue tomorrow on link state routing. We'll start on link state routing. I posted also what is called the exam booklet, which is the only document that will be given to you during the final exam. The final exam, like the test that you're used to, is without document. Now, that might cause some anxiety to some of you. So to remove this anxiety, we will provide to you the document that I posted today. So don't print it. We will print it for you because we don't trust your printing. Next week, we'll start the module on congestion control. Next week, quite exceptionally, I will not be here. I will be attending the IETF, which is the meeting at which people discuss TCP-IP protocols. I'll give a presentation on deterministic networking. And therefore, quite exceptionally, the lecture will not be given by me, but will be given by Dr. Elena Stey, whom you know already from the labs. And the lab will continue on OSPF. This is where we stopped last week. We've seen that with OSPF, all routers share a global vision of the network in which they are, which is called the link state database or the topology database. And once they have this vision, they can compute using the shortest path graph algorithm, which is typically Dijkstra, which is Dijkstra in OSPF. They compute the shortest path. And we have seen that most versions of OSPF will support multiple shortest path, which is visible here. This is the routing table at A. So A has computed all those shortest destinations that are given here. In particular to D, the distance from A to D is 30, but there are two paths, one via C and one via F, E, D. And since the costs here are 10, 10, 10, and 10, 20, they are equal costs. This is allowed in IP. You can have multiple paths. It's even a good idea because it means that the traffic from A to D will be able to use several existing paths and therefore do some kind of load sharing between the different paths. Yes?
Do not have N6 in the table?
We don't have N6 in the table. Where is N6?
Between D and E.
Between D and E. Yes, of course, it will be also in the table. It's only, there will be a destination entry for all possible networks, including N6 also. Right. So I've said that this is a good idea to have multipath to D, but still, how should a router like A handle the case where it has two entries to destination D? So assume A has a packet with an IP address that is destination D, or another network that's attached to D such that there are two next hops. What should A do in such a case? So I'm asking for your opinion. The poll should be open. I close the poll in 5 seconds. And the majority says A, send them to the next hop with equal probability, which makes sense globally, but perhaps not always. What if all of these packets are coming from the same source connected to A, that is, or connected somewhere, that is on the path between, where such that A is on the path, and it's one TCP connection, for example. So if all packets are from the same TCP connection, is it a good idea to send them on different paths? What do you think? They can be maybe reordered, exactly. So TCP, as we know, is a bit clumsy in the sense that if packets are reordered, a bit reordered, it might understand it's a reordering, but it might not. We don't really know. So TCP will continue to work, but perhaps the performance of TCP will not be optimal. So certainly you can do A, but perhaps we can do one epsilon better. What would be this epsilon better? Yes?
Open connections.
Open connections. But A is a router. A is here. A is somewhere more precise. Is a router, right? Sending traffic to D. A does not open a connection to D. It's the source of traffic that opens a connection to something that may be D or a network attached to D. So that is not possible. It would not be desirable even if it would be possible, because a router doesn't want to be managing all the complexity of TCP on behalf of the source. But perhaps we can do something which keeps the packets together while, in average, dispatching them with 50% quality on each path. This is possible if you can observe in the packets the TCP headers and the TCP ports. So if you can do that, which we know NATs do, for example, we typically can do it, except if the network, everything is encrypted. For example, we will talk at the end of tunnels. If you use virtual private networks, it might be that all the traffic is encrypted. That might be more difficult. But in general, it is possible to observe the flow of the packets by looking at the combination of source IP address, destination IP address, port source, and destinations. And if you can do that, then obviously, as a router, you will manage to have the same decision. You may randomly choose one path or the other, but you want to do it in such a way that packets of the same flow are given the same decision. We have seen that NATs do that by keeping state information. When a NAT sees a packet for the first time going from the LAN to the WAN, then it will remember who in the LAN is sending this packet, will change the addresses and port numbers, and has to remember. So a NAT is stateful. If that would be the price to pay here, we would not do that. We want routers to be stateless as much as possible. If you want to be stateless and do the same thing as stateful, there is a very well-known trick to that. It is to use hash functions. So if you, for example, a hash function can be seen as something that takes a string and returns a number between 0 and 1, such that it appears to be completely random. If I change one bit in the port numbers, or if I flip one, if I do any change to the port numbers, it's completely unpredictable what is the new value I will have. If it's completely unpredictable, it would be called a cryptographic hash. We don't need probably that level of sophistication. Here we need something that appears to do something completely random. So the value of the hash is between 0 and 1 and is uniformly distributed between 0 and 1. Then if you take for M, the string M, a flow identifier, the combination of source and destination addresses and port numbers, then that will make the job. I will route based on this. For example, if H is less than 0.5, I use the first path. If it's larger than 0.5, I will use the second path. And with probability 0.5, I'll use one or the other. So many routers do that. It's called per-flow load balancing. Not all. We will see that in the lab. Depending on which version we use of Quagga, we might or might not have that. But that is certainly is a desirable approach if you use equal cost multipath routing. The next topic we need to see in detail is how OSPF manages its promise of being dynamic. OSPF is a protocol that is discovering the topology and also, of course, adapting to it. The topology changes due to additions. You add a new node, you remove a node, but the most frequent changes are failures. Failures of a link or failure of a router. Entire failure of a router, the room in which the router is sitting is flooded, you lose it. Or more frequently, there is a bug or a process crashes and then it doesn't respond and it needs to be rebooted. Hopefully some mechanism will detect and reboot it, but before that happens, the router is down. So failures are the major things that any routing protocol has to address. They are detected if by anything else, certainly by the OSPF's hello protocol. Remember that in OSPF, a router has to discover who the neighbors are, who are the other routers that are on link with this router and speak OSPF and are in the same domain, in the same administrative domain. And a router maintains an adjacency with all the neighbors. The adjacency means that when a router joins later, for example, it copies, it synchronizes its topology database, and also it periodically sends messages to check that everything is still okay, that the link is up and going. So this is done by the hello protocol, which is a very classical mechanism for such things. So if a router crashes, or if the link between two routers crashes, or if a router process does not respond, then there will be a failure of the hello protocol. After a few seconds, one of the routers will detect that this neighbor doesn't exist anymore. So it is perceived as a local change to the topology. And then OSPF will flood this new information to the entire area, and therefore everybody in the area will know that this router doesn't respond to this one, which means this link doesn't exist, or this router doesn't exist anymore. After the flooding has converged, so flooding in OSPF networks that are typically there are not millions of routers in an OSPF network. In an area there are perhaps a few tens, maximum 100 routers, so flooding will be very fast. And then every router will recompute the shortest path once it has perceived that there is a change in its topology database. Question?
Yes. Would it not be desirable to wait until we actually have to transmit something to do the recomputation? If we crash a lot of time, if we have no traffic, then we might want to just wait until we really have something to send so we can keep the first path.
So the question is, why do we do it automatically and not when there is something to send? Well, it depends on what kind of router you are. The kind of router that would do it on demand is a fairly rare occurrence of a network where there's not much traffic. And there is a protocol that does this called AODV, on-demand distance vector routing protocol. It's not using link state but distance vector. So for ad hoc networks that are made of devices that are connected together, they will typically do that. They will analyze the changes when there's a need to analyze it. But for most routers otherwise, it's not the case. I mean, when you do Wireshark in any network situation, you see lots of traffic always. There's Dropbox, for example, that's constantly keeping updates of everything. There's lots of protocols everywhere. So this assumption would not be a valid one for most routers. Routers typically have a lot of traffic always to transfer. So they know if a route is broken and we cannot use an existing route, I have to fix it as quickly as possible. Let's see a small simulation on how things would happen. Here I'm showing a small toy example with 4 routers, and I'm showing on the left here the link state database, which is the same in steady state. So this link state database is shown in graphical form. Of course, in OSPF it's not graphical, it's a collection of all the link state advertisements, but we can represent it in a compact form in this way, and the routing table here. So we see, for example, that D, which is here, if it has a packet to send to A, it has 2 paths, one that goes via C, which say here called west interface, and one that goes via the north interface of D. I'm assuming here that north is to the top, which is not quite right, but is very frequently done. Assume that this link crashes. It's broken. And this occurs at time t0. Now, what will happen next is difficult to know. The system is distributed. There are 4 routers. So the ordering of events may be completely different from what I'm showing here. This is just a cartoon explaining one possible illustration here. So I'm assuming here it's A that detects it first. A perhaps using the hello protocol I mentioned. The hello protocol is not necessarily synchronized, so it may be that A detects it before B. When I say before, it may be 20 milliseconds before B, which is for us not visible, but if we do a detailed Wireshark, we would see all those differences. So I'm assuming here that A detects the failure, So A will update its local interface and neighbor database, and therefore also its topology database, and will recompute shortest path, for example. A that had the shortest path to D that was via B is now deleted, so the red thing here is deleted, and also the path to B now will be recomputed. B is, according to what A knows, is now reachable via C. So this is what A will do if it does things in the order I said. A will also, in parallel to that, will send a link state advertisement, an update of its link state advertisement to C. So A had before sent link state advertisement to C and B, who flooded them to D, and now this is changed. So remember that a link state advertisement is the local view that a router has of all its neighboring environment. So this has changed. This is sent to C. C will do something when it receives it, but it has not yet received it. So what happens now if, for example, a packet is sent by C to A, by the forwarding engine of C, then the packet will go to A and return to C. So there is a routing loop. During this transient period, there is a routing loop. Of course, we hope all of this takes a few tens of milliseconds, but this loop exists here. Also, D, that doesn't know yet anything of that, continues to send traffic to A via the two paths via C and B. So half of the traffic sent by D to A will be lost here during the transit. This is something we cannot avoid. There is a failure. In the time we're trying to recover from it, things don't work normally. Question?
Does the hello protocol have two distinguished paths to detect the failure and flood the messages to hello one that it's changed?
Does the hello protocol do different things like detect the failure but also flood the changes? No. The hello protocol is just a ping. So router A sends a ping to B, saying to B, please respond. B responds or not. It's like when you use ping. If you see no response after 3 pings, you declare B dead or unreachable. That's all that the hello protocol does. The rest is done by OSPF, sending an update of its link state advertisement. This is done by OSPF, not by the hello protocol. There are other mechanisms, by the way, than the hello protocol. There are also protocol mechanisms that are at a lower layer. For example, typically the Ethernet adapters have also mechanisms to detect the absence of a link. If, for example, it is the link that is physically broken here, there is no power anymore on the Ethernet adapter, and that will be visible immediately. So that may trigger before the hello protocol. Now, sooner or later, C will receive this message. So C has now a new vision of the topology database. That was the topology database seen by A. We see that the different topology databases in this transient period are not synchronized. They're not exactly the same. Now, C has received the change. So C knows the network is like this now. It knows A has lost a link to B. Therefore, C will redo its shortest path computation and will find that the best path to B, which is only one, is now via D and not via C or D like before. So the routing loop in particular between A and C is broken, but the rest of the network still doesn't know, so D continues to send some traffic to A via B here. Then D now has received this link state update, this link state advertisement update from A, which was repeated by C. Therefore, D now knows about the new topology and has this vision of the topology database and will compute new routes. Here, I'm assuming that in parallel to that, B woke up and also detected the loss of the adjacency. So B, at the same time, here does its update and sends an update to D, and that will also be flooded to C and A, so that eventually now everybody agrees and has exactly the same topology database, and the new routes are computing. So at this point here, the network is stable again. How much time does this all take? The processing itself is very fast, except if the links are extremely long, which is not typical. So the processing itself typically takes less than a second over all the nodes. What may take some time is the detection. If the hello protocol is used, depending on the hello timer value, you may have to wait for several seconds. So OSPF failure recovery is not real time. During the recovery phase, which may take 1 or several seconds, the network has lost connectivity. But the good news is you have nothing to do. All of this operation is entirely plug and play. Perhaps we'll come back to this question in a minute. So we have seen that OSPF is able to compute routes and react to changes. Let's say a few words about the security of OSPF. So how could you attack a routing protocol? Well, an obvious thing is to send invalid routing information. If the system is not protected, you could pretend to be a router, and then you could attract all traffic to you, where you could try to sniff all things and perhaps kill some traffic if you're trying to buy some tickets from a popular ticketing site and nobody can reach because there's an overload, then you can kill all traffic to that ticket site so that you are the only one able to go there. So you can do things like change network paths, disrupt network operation, and what is something very frequent is denial of service attacks, right? Against OSPF routers, for example, that will be unable to work properly. So the key thing to prevent this is to make it impossible or very difficult for an attacker to pretend to be an OSPF router in this network. I would not say state of the art, but the current way of doing things is to do authentication. So how does it work? Well, the simplest way is to have a password that you put in every router. And this password, which is the secret key, is shared between routers that have to talk together directly, that are on link. So if you have on a link 2 routers, which is a very frequent case, or if you have on a LAN, a shared media, or a bridge LAN, you have 5 or 6 or 10 routers, which may happen at the backbone of your network, for example, then all those routers that are on the same LAN, so that will be neighbors in the sense of OSPF, have to have the same secret key. That's the weak part of it. Once they have the same secret key, then you simply sign everything you send using, for example, this cryptographic hash. In general, you need to have a hash function. Now, a cryptographic hash, when do we say that a hash function is cryptographic? A hash function is something that turns an arbitrary string, or a string of a given size, into a number between 0 and 1. And if it's a hash, it means the number appears to be uniformly distributed between 0 and 1. Yes?
Because in an ideal case, the original data cannot be recomputed, so it's just a hash.
The original data cannot be recomputed. It's true, but we need a stronger, so every hash function practically will have this property, except, so ideally you want that it's very difficult or impossible to reverse the hash function, given the hash value, what was the thing, what was the input. In general, even for non-cryptographic hash function, that's very difficult. A cryptographic hash function is one where collisions are virtually impossible. A collision means forging 2 inputs that will produce the same output. That's the strongest definition of cryptographic hash function. But you're right. It means it is practically, for an attacker, impossible to forge a message that would cause a given hash function. So if you have this, then whenever there's an OSPF message, so when a router speaks to another, sends a hello or a link state update, for example, this message is taken as input to the hash function, together with the IP source address of this router, and together with a sequence number for avoiding message replaying. All of this is input to the hash function that gives the value. I said a value between 0 and 1. You code it on 256 bits, for example. That gives what is called the digest. Now, if you are a neighboring router, when you receive this, you can verify that the message that you have received has been sent by somebody who knows the secret key. Because if the cryptographic hash is collision resistant, there's very little probability that you're able to forge exactly this message with the correct sequence number in particular that would have exactly this value. There are a few other additional details. The sequence number has to be resistant to crashes, because an attack could consist in replaying a message that was played in the past and that was valid. So an additional sequence, bell and whistle that we add to this is that this number are strictly increasing forever, which means that there is part of the number is stored to disk. So when a router reboots or a router process reboots, it reads what is on disk, the previous number it used, it adds 1 to it, and this to the what is called the boot count, and this boot count is part of the sequence number. So of course sooner or later this will wrap, but this is encoded on 64 bits in total, so it will wrap only well after the router has dissolved and has been recycled probably many times. This is the best you should do today. In the lab we will not use that, we will use older versions because the versions we have in the lab don't support this. There is a weak part to it, which is that the secret key has to be the same in all routers, right? Which is a considerable trouble. It means if you interpret the secret key as a password, you have the same password in multiple routers, and the password has to be different whenever you have different groups of routers that are on link. So managing all these passwords is some complicated stuff. How would you manage it concretely? In the lab, we will ask you to give a password, and that will be good enough. But if you have to run this for an enterprise, probably you don't want to write in a file or on paper what are all the passwords or the passphrases that correspond to each of the router pairs, because this file, you will need to keep it somewhere. It has to be very secret, etc. Yes?
Key cryptography and public structure.
Yes, so the classical method to go beyond that is to add to this an additional layer based on the public key infrastructure and certificates, where the certificates could be used to check and also create the keys in a systematic way. So all you would need is to find a public and private key pair for every router, but the private key, of course, has to be kept secret in the router, but no one else needs to know the key than the router in which it is placed. So that's all we'll talk about security, because I always put some hooks on security, but of course many of you might be interested in taking a security course next semester. Question?
Yes, so there is a group of routers who use OSPF and Computation, and whenever a new router was to link to this group, he also has to have the same key.
So if there is a group of routers that uses OSPF and a new router comes, does it have to have the same key? No, not exactly. It has to have this router will connect to one, or let's say two routers of this group. For each of those pairs, it will need to know the corresponding key. So if I'm a new router, I come and I join to you and to you. On each of these links, there is a shared secret key, and I need to know those two secret keys to connect. The OSPF we have seen is the primitive version. That's the one that works in a single area. OSPF has been made, in fact, to work in very large domain. In a single area, we flood all information to all routers. So there is a limit. If the network becomes very, very large, you perhaps want to optimize a bit on this. So OSPF uses a hierarchy of systems with two routing levels. And with that, it's able to scale to practically networks of any size. We will see another example of hierarchy. We will see that BGP is used in the internet to interconnect administrative domains. OSPF is always inside one administrative domain. So you don't use OSPF to interconnect all domains of the world. You use it if you have a very large domain. A very large domain is typically enterprise networks that are very large, or very large enterprise networks are ISPs, Internet Service Providers. OSPF uses the hierarchical domains are called area, and OSPF uses a very simple hierarchical principle where there is one area that must be the backbone, it's called area 0, and all other areas must be connected to the backbone. So it's a primitive hierarchy. There's not an arbitrary tree of any kind of shape. It's just a two-level hierarchy with a root, which is the area, and the leaves, area 0, that are the other areas. And all inter-area traffic has to go through the backbone. So if A1 has some traffic to send to B1, it knows the job of A1 is it has to go through the backbone, through area 0. That's the principle. Inside an area, area 0, area 1, area 2, here we do exactly what we've seen so far. So we use link state inside an area. Now, to go beyond, then we don't do exactly link state, or a variant of link state. First, how do we go beyond? Well, by having routers that are called area border routers that belong to multiple areas. Here, X4 belongs to area 0 and area 1. This is how the two areas will be able to be connected. That's different, for example, from BGP. BGP is used to connect two domains, and when you connect two domains, typically you have one BGP router in every domain, and they talk over the border. Here, we're all inside one domain, so there's no reason that everybody has their own router. X4 all of this is managed by the same network administrator group. So we can share the border. Then the area border routers, like here we have 4 area border routers, X3 and X, I guess it should be a 5. Those numberings are a bit bizarre. So X1, X2, X3, X4, X5, X6, so the numbers should all be different. The 4 border routers here inject the information they've learned from one area into the other area, using mechanisms we will see in detail here. So let's see an example. We start with area 2. All routers in area 2 do the normal link state job we've seen before. So they share their topology database, and the topology database is illustrated by this gray box here. This network map, which is the map of area 2, is when things are stable, so except during transient periods of failure recovery, is shared, is the same between the 4 routers X4, B1, B2, X6. The routers share the information, but they also compute shortest paths. That's their job. So, for example, X4 will compute its shortest path to N1 in area 2 using Dijkstra. So it will compute 9 plus 1, 10, and well, that's 9 plus 1, that's 10, that's the shortest path, and the next hop is B1, and to N2, X4 will compute 6 plus 9 plus 1, 16. So that's what X4 gets using Dijkstra's algorithm in the area. Similarly, X6 has computed another Dijkstra computation. They have the same topology database, but we have seen that every router in an area compute their own shortest path tree, which is different because they have a different vision of the area, even though they have the same map. They're at a different location. So that's the business as usual inside an area. Now the trick is, we don't see it very well, it's in yellow here. The trick is X4 and X6 have a dual role. They belong to area 1, but also to area 0. So now if they take their area 0 hat, they will say, I am in area 0, and I know of prefixes N1 and N2 that are treated as though they were external prefixes. OSPF doesn't call them external, they're inside the domain, but they're outside the area. So they're called inter-area routes. So X4 will use link state advertisement to give this information to all routers in area 0, saying, X4 would say, I am connected, I have a distance to N1, which is 16, which is 10, and a distance to N2, which is 16. So they will give the distance information. They don't need to give the next hop, they just need to give the distance information, which is what is illustrated here. So in some sense, X4 will speak to the rest of area 0 as if it would be directly connected to N1 and N2. X6 will do the same. So we see that N1 and N2, it is as if they would have dual connections to those two routers with different costs of attachment. Through the flooding mechanism inside area 0, all routers in area 0 will discover those values. So, for example, X1, X3, X5 will know that X4 knows of N1 and N2 with certain distances, and X6 as well. Now, what could routers in area 0 do? Well, they could rerun Dijkstra. After all, those are changes, those are additions to the topology database. So we could rerun Dijkstra with those added links, but it's more efficient to use an incremental computation since Dijkstra has been computed already. Instead, we use this alternative here, which is in fact the same formula that is used in distance vector. It's called the Bellman-Ford recursion. The Bellman-Ford formula says that the distance from me to some destination is the minimum of the distance from me to all my neighbors or all the routers I know that already know how to go to that destination, plus the distance from this border router to the destination. If I take the minimum of all these, then I will find the distance from me to this destination. Because I know in this case, the destination N1 is an inter-area destination. It is not in area 0. If it would be in area 0, I would have obtained its cost by using Dijkstra. So if you want, this can be seen as an incremental Dijkstra computation. But we don't use the Dijkstra algorithm to compute it. In this case, it's very simple. Router X3, for example, knows that there are only two routers in the area that have advertised a distance to N1. So it has to compare the cost of going through each of those two routers. So it's linear complexity. So X3 will compare the cost of going to N1 via X4, which is this guy, and via X6, which is this guy. We find 23 and 34. 23, which is the cost of going from X3 to X4 plus X4 to N1, and from X3 to X6 plus X6 to N1. So it finds the minimum of the two, and the minimum is 23, and for N2 the minimum is 22. Further, when we compute this minimum, we not only compute the minimum, but we remember which of the border routers gave the minimum value. In this case, there's one, and the border router is X4. So we know that from X3 to go to N1, it's shorter to go via X4 here. Therefore, X3 in its routing table will decide that the next hop to go to N1 is equal to the next hop to go to X4. The next hop to go to X4 is already known from Dijkstra's computation. So this is how X3 will know two things. It will know the distance to N1 and also the next hop to N1. Without having seen, compared to what we saw before, X3 doesn't have any of the details of area 2. It knows nothing of area 2. It knows only the cost from X4 to N1. So it's a way to share the job. This cost is computed inside area 2. If there are changes inside area 2, we need to recompute those costs. But the complete Dijkstra computation is split, if you want, into smaller computations. So this is how the information goes to area 0, which is the backbone, but it's not over. We need also the information to go to all areas, but from the backbone it will go to all other areas, because any area must be connected to the backbone. For example, X3 and X5 are both in area 1 and in the backbone. So X3 has done the computation I've shown before. X5 did a similar computation. So X3 and X5 has this information which is in yellow and hard to read, but they show, for example, x3 has the two values we've given before, distance 23, 22, and x5 has the distance 22 and 16. So x3 and x5 inject this information into area 1. It's the same mechanism as we saw before inside area 0. By flooding in area 1, all routers in area 1 have this topology database, so those distances to inter-area routes are put in the topology database as special entries, and the same process will occur. For example, A1 will compute what is the cost of going to N1 and N2 by comparing the cost of going to X3, which is known from the result of Dijkstra's computation inside area 1, plus the cost of going from X3 to N1, which is given by the topology database here. So it will compute the two and will find a distance is 33, and the shortest path consists in going via X3. This is how OSPF really works with this multiple area stuff. So, one or two quick questions to check where we are. First one, this one. When applying the Bellman-Ford formula to compute the distance from self to N1, where did the router, such as A1, get the pieces of information from? Close in 5 seconds. And the majority has the correct answer. It's from this combination that is shown here. Correct. Oops. Let's conclude this first hour with this additional question. Time to close. And the majority is right. The immediate neighbors detect the loss of agency, of adjacency, and inform everybody who can receive the information through new LSAs. It's not the hello protocol that will have everybody detect the crash. The hello protocol is only local, so it's only the immediate neighbors that will send it with the hello protocol. And of course, the mechanism of OSPF is to use the topology database. If the network is partitioned, for example, there are multiple failures such that we have two sets of routers, then what will happen is that only those networks that are in the same partition will receive the information. So this would be a very severe case, and there are special mechanisms to handle that, as we might discuss in detail. Voilà, that's the end of this first hour. You know practically everything you need to know about OSPF to do the lab. So now your job will be to discover how it really works in reality. OSPF is really the most widespread routing protocol, so practically any enterprise you might be considering is very likely to use OSPF. We resume in approximately 15 minutes, and we'll continue with a few more topics on routing. So we're ready to restart. And we restart with another quiz. I close the poll. And the majority says B, which is correct. X3 belongs to area 0, has one topology database with a map of area 0, and another topology database for area 1. So it has two topology databases that are not injecting from one into the other directly. If we would do that, we would be doing a big link state update. But there are summary link state advertisements that are used to make the link between the two. So as I said, the summary LSAs, those are the informations about network prefixes and how they are reachable. An example is this one, for example. That's an example of a summary LSA put in graphical form where X3 knows that X4 is reachable with a certain distance. Voilà, as I said, that's pretty much all we will see in the lecture about OSPF itself. The rest is in the lab. What we will do in this second hour today is three. We'll talk about other uses of link state routing. We'll talk then also a bit about software-defined networking. And I think, if time permits, we'll also talk about more theoretical performance and optimality issues in routing in general that are not necessarily related to OSPF. So the method we have seen exists in practically only two routing protocols that are very similar today, OSPF and IS-to-IS. OSPF is perhaps the most widespread. Now, OSPF, as we saw it, is used only to compute shortest paths. But as you have a topology database inside an area, at least inside an area, you can do much more fancy things. For example, you can do what is called multi-class routing, which consists in computing not one shortest path, but one shortest path for every type of traffic, if you're able to quantify what happens on links. If some links are larger delay than others, they are less suited for audio calls, for example, for IP telephony. So you may want to find different shortest path for different type of traffic. This is also called sometimes, this is also used for a wide range of specific things. I'm just quoting one here called explicit routes. Explicit routes are almost the same as source routing. Perhaps you remember what source routing is. What is source routing? This is not source routing. This is me not pressing the button for the light, I hope. Yes. Source routing is, yes? Yes, it is a mechanism for routing where the routing is entirely contained in the path. That means it's the source that has the job of computing the route. This is the strict source routing definition. An intermediate thing, which we called edge routing, is when an edge router computes the route. So only routers that are at the edge of a domain compute a route. And once they have computed a route, they can put the entire path, not just the next hop, in the header. It's possible because an edge router, or any router in an OSPF area at least, has a complete vision of the entire domain. So it can compute not just the next hop, but an entire path. So it can put an entire path. What's the interest of that? Why would anybody care about doing this? Well, one thing it guarantees is written here. Certainly, it makes loops impossible. The route is computed and is put in the packet. So, of course, you assume that when you compute a route, you don't create looping routes. We have seen that during transient periods, there might be loops that exist for short amounts of time. If you absolutely want to avoid this, for whatever reason, some real-time application may require that, for example, then computing the route at the edge, at the first router that hits the domain, is a way to guarantee this. Of course, if there is a failure somewhere and the route is not valid, then the packet will be dropped. The routing will not work. But we will avoid routes. That's one other of the major uses of this. So this is used in networks for industrial environments, for example. Here is another widespread use of link state that we will not see in the lab. This is for bridging. Right? Bridging, in principle, doesn't use a routing protocol. By definition, routing is for layer 2, bridging is layer 3. Routing is layer 3, bridging is layer 2. So by definition, anything done at layer 2 is not a routing. But this is a very dogmatic thing. If you look at what the algorithms and the methods that are done, a layer 2 network or a layer 3 network very often have common problems, except perhaps a layer 2 network will never be as large as the internet. But other than that, the problems are very similar and overlapping. That's one of the annoying things in TCP/IP networking, that there's two layers that are largely overlapping and sometimes doing similar things. Here's an example. Perhaps you remember when we talked about Wi-Fi at PFL, I mentioned how many Wi-Fi base stations there are at PFL, and I'm not sure about the exact number, but it certainly is above 1,000. So there's around 1,000 base stations that each of them, you can think of them as a bridge that gives access to people at EPFL. And EPFL is a medium-sized campus. It's not a big campus worldwide. And the way a Wi-Fi manages things is that when you connect in the morning first thing, you get an IP address from the base station using DHCP at the base station where you are. When you move from place to place on the campus, you will keep this IP address. And of course, now you are at a different location on the campus, so you have to make sure that the same subnet, which is the place from where you got your IP address in the morning, is able to exist at different places on the campus. And the concept for that we have seen in the MAC layer is called virtual LANs. Virtual LANs are the mechanism by which you can have two hosts that are at the two ends of the campus be in the same subnet. So we do this, for example, for the Wi-Fi network. So you have, for example, the red virtual LAN exists at 3 places in the campus and the blue at 3 other places here. Now, a simple way to manage a virtual LAN is to have a big set of bridges everywhere that connect, that do spanning tree, one red spanning tree, one blue spanning tree. But that is perhaps not very good if the number of bridges is huge, like in the 1,000 order. So what is done very often is to use routers to do the bridging. So routers, assume here you have a number of routers here that are, or boxes that are both routers and bridges, to which are connected a number of virtual LANs. And then the idea is, if I have a router here and a router there, and I have a red virtual LAN that adds the 2 places, I can use what is called a tunnel. What is a tunnel? Apart from a hole in the Alps that in Switzerland we love, in networking.
So when you pack layer 2 frames into layer 3 packets.
Exactly. It is, for example, when you put layer 2 frames inside layer 3 packets, which normally you don't do. Inside layer 3 you have a transport packet, not a MAC layer packet. But you can, for example, if you establish a connection between R1 and R7, and whenever a red packet here has to go from a host here to a host there, you can put it inside an IP packet with destination address R7. Of course, a protocol type that would say, oh, this is an encapsulated virtual LAN packet. It's not a transport layer packet. So that this packet will be received by R7 that knows it is now a MAC frame. And then it will put it on its bridge side of things. So it is as if we would have a physical link between R1 at 7 and R7, as if there would be 2 bridges connected by a physical link. But now they are not, there is not a physical link, there is just IP connectivity that gives the same thing as if we had a physical link. It's called a tunnel. We'll come back to tunnel in the last week of the course. Now, the problem is if you have just 2 or 3 locations for each virtual LAN, so 6 in total like here, you can configure all of this manually. If you have 1,000, with 10,000 people that creates perhaps a lot of flux and movement everywhere. How do you know how to send the packets to where? So how do you do those tunnels automatically in particular? So for example, whenever somebody who appeared here in the morning has moved and is now here, so this router will say, oh, I am this guy belongs to this virtual LAN, so the configuration of the Wi-Fi subsystem will know that I am on this virtual LAN, so all of a sudden R7 has a packet that belongs to the red virtual LAN. How? Now R7 needs to do something that allows the virtual LAN pieces to be connected. I propose here a few possible answers. How could you use, and now assuming all the routers are using link state routing. Could you make use of this link state routing to solve my bridging problem? I propose two solutions. Which one do you prefer? I close in 5 seconds. And the majority says A, which is a good solution. Indeed, since all the routers have local information, they say who is all of a sudden showing up with a given virtual LAN label that I didn't have before, then this can easily be added to the LSAs. Then through the update mechanism, all routers will have, in fact, the map that I'm drawing here will be visible to all routers, which are in fact combined bridges and routers. So R1 will know exactly this map. So it will know there are red people at R7 and R5. So for example, when R1 has a broadcast to do in this LAN, it knows it has to send it to R7 and R5. If it has a packet to send to a destination that it doesn't know, a MAC layer destination that it doesn't know where it is, it will use it encapsulated or in tunnels. Encapsulation or tunnels are synonyms. The syntax is different. We have a tunnel when we use encapsulation. R1 will send encapsulated MAC layer packet to R7 and R5, for example, and will therefore create the equivalent of a spanning tree here. That's an example that is used in fact, two standards. The problem in networking is that there is not one solution to do the same thing, but multiple solutions, and it's not always very clear why they all exist. So the solution that I described here is called Trill, which uses IS to IS, but IS to IS for us is the same as OSPF. And there is a similar thing called shortest path bridging. Bridging, as we have seen it, is called transparent bridging. It uses learning and the spanning tree protocol, which is, I would say, the cheap bridging. Now, if you want a more expensive bridging, then you can do routing, but you still call it bridging, and it's called shortest path bridging, where you do essentially the same as OSPF. So every bridge in this shortest path bridging thing will compute shortest path from one node to the next, and will build shortest path tree, like is shown here, and this will be much more efficient than transparent bridging with a spanning tree. Why will it be more efficient? Why is shortest path routing or shortest path routing more efficient than the way bridges organize themselves when they use a spanning tree? Well, the name tells it all. A spanning tree is a spanning tree. That means the entire, when we use the spanning tree protocol, we create one tree of the entire network. Remember, for example, if the network is a ring, we will disable one of the links to force the ring to become a line, an open system that doesn't have a loop. Right? If we use shortest path bridging instead, we will go on the ring to the shortest path, which may be one side of the ring or the other side, depending where we are going. So we use all the links that are available, not just use them as backup like spanning tree is doing. But of course, this is at considerably more complexity. We have a topology database in every bridge, which is orders of magnitude more complexity in terms of CPU and processing than we have in a transparent bridge. Voila, those are very quickly possible uses of the same ideas of link state routing. Now we jump to something radically different, which is conceptually much, much simpler, which is called software-defined networking. Here is an illustration that I take from this reference. This is a recent ACM SIGCOMM paper, which is illustrating the kind of things that happens in large networks today, or say in managed networks today. So networks are about computing connectivity and shortest paths, but also about managing and observing what happens. Here is an example where there is a sudden traffic surge that we suspect to be a denial of service from A, D, and E to destination F. Right? So we see a lot of traffic here from those sources to F. That's the red traffic. What should you do if you're running this network? All of a sudden you see 1,000 times more traffic than your statistics are normally showing. What do you suspect? An attack. It could be an attack, it could be a denial of service or an infection or something, but you're not sure. It could also be that there's a very, very popular website here, and there was a link on Facebook saying, and everybody's watching that, so perhaps it's an attack, perhaps not. Yes? Exactly, there might be a deadline for submission of paper, or we've just opened a reservation site for tickets for a football match or for the Olympic Games, and then everybody's going there to buy the tickets. Exactly. So it may be a flash crowd or a denial of service, you don't know. How can you know? Well, if you just are counting packets, there's no way you know. So you have to analyze the content of packets. So you have bought from a company an intrusion detection system or an anomaly detection system that is able to do deep packet inspection. But those systems are not able to do it on all traffic at all periods of time, because that requires extensive processing. Here it's called a packet scrubber. It's looking inside what is in what's in packets. So what you would like to do now is to be able to force the red flows to go through here, because your packet scrubber is here between B and C. So you would like a mechanism that allows some flows to be routed specifically. That's the goal of software-defined networking. With the things we have seen so far, we have a fairly non-distinctive way of routing traffic. The principle of IP is we route based on IP address, not on a per-flow basis. But for practical reasons, once in a while, you may want to alter these things and give special routes. So this is called per-flow forwarding. And most routers that we have today, we can do things like IP route or rules, and we'll do some of them in the lab. In fact, we've done some of them when we looked in the very first lab with IP tables. We've seen it's possible to manipulate exactly what happens. So routers today can have a variety of mechanisms. One that is very much used in the context of software-defined networking is called rules. So a rule means that in addition to the routing table, that's the principle of IP networking, you may add at some point in time rules. And the rules typically have priority over the IP forwarding table. So when a packet comes, what you do is you look whether there is a rule that matches this packet. If not, you use the IP forwarding. Here's an example. We are zooming on router R1 here. This is its routing table. The routing table is a default route, 0/0, that goes to 1. That's the default route for this. It has a second route that says anything that starts with an A goes to 0, that's in this direction. Anything that starts with a C goes to 3 here. So in principle, you never route to this link. So router 1 has a very simple job. it has a local network A that is here, A and C, and everything else goes there. This is an edge router, typically. But it also has a backup link, but this backup link is used only for special purposes that will be used here for the flow table. Let's say backup or a dedicated link. The flow table has the rules, and the rule is a bit like a grep representation. We have something that must match the flow of the packet. The flow of the packet is by looking headers. All the headers you can find, this is specified in the rule. For example, here, the destination IP addresses should be b.d.anything. So typically it would be written, for example, 128.178.156/24. So if the first 24 bits match this, this is part of the rule. Another part of the rule in this case is the input interface on which it's coming. So here that means anything that comes on input port 0 has a destination IP address bd.anything, matches the flow spec of the rule. And then we go to the action part of the rule. The action here is send it to output port number 2. This is how we can forward packets specifically to some flows here. There is a priority field because as soon as you write rules, I don't know if you've had the experience already, it's practically impossible to write rules and be fully consistent. So one way to be consistent is to improve the chance of consistency is to add priority. So rules typically go together with priority. The higher the rule, the more important it is. So the rules are looked up by order of priority. If there is a match at a high priority rule, we stop. If there would be, so that's the order in which we check the rules. Another way to put it is that if something matches the 2, then it is the one with a higher priority that we test before. That's the one that will apply. So assume this is the flow table at R1, and we have a packet from Lisa. Lisa is here, that is going to the enterprise server here. And also packets from Homer to the enterprise server. Which way will they go with that set of rules? I close the poll. And the majority says none of the above, which is true. That's the correct answer. Why is it? Well, Lisa's packets are coming on port 0. So what do they match any of the rules? Yes, they match the first rule here, so they will go this way. They will go to port 2. Homer packets don't come from port 0, so they don't match this. They match the second rule, but the second rule says drop. Means those packets are killed. Ping. Homer is not supposed to talk to the enterprise server. So what these rules are enforcing is that the only guys that can connect to this must be on this interface of the router. So this is the kind of security you can implement if you control the topology of your network. The effect of these rules is to allow the traffic here only if it comes from this, which is the only place where you're supposed to work on updating the precious information that is here, for example. So software-defined networking is about automating such rules. So a practical network today will have things like OSPF, BGP, things like this, that are configured by the mechanisms we'll see in the lab. Plus, in practice, if you want to do a number of ad hoc things, like those ones here, then you need to talk to each of the routers and perhaps the switches, which you can do with the kind of manipulations we do in the lab by SSHing into each of the machines and configuring them. But of course, this is not extremely nice. If you're Google and you have a data center with 3,000 switches, you don't want to SSH into each of them. I'm pretty sure you will have problems. So what do you do? If you're in a case like this, you're working at Google, you have 3,000 switches to update constantly. What do? Do you hire 200 people to do the SSH? Or do you hire 5 software engineers to write scripts that will automatically SSH? Right. This is what SDN is about. SDN is about being able to write scripts in Python, typically, that will automatically talk to the switches and the routers to do the things. You can do it the Google way. If you Google, you can do it your own way. But you may also want to do it in a standard way. Instead of when you write, if you write software for doing that, you will need to invent a protocol between your script that is on your machine and the different switches. You will send commands to the switches. You need to define how you send commands, how you do that. So the way this is, so software-defined networking is exactly about specifying an interface between a controller and a local controller that is in SDN called a listener that resides typically on switches, also on routers. This was originally developed for switches in the big data centers to, as we said, to have special ad hoc rules. And the protocol is called, for example, OpenFlow. So OpenFlow is a protocol that specifies the kind of command you can send to a router and a switch without having to write your own SSH things. So in the lab, for those of you who will do the research exercise part of the lab, we'll ask you to look at a specific central controller and see how you can achieve certain goals with it. If we have SDN, we're able to control everything in our network of switches or routers. Now, assume our network is a network of routers. SDN is primarily used with switches today. Some people start using it with routers. Let's assume, for the purpose of this question, that it's used with routers. If we do that, I mean, why do we continue to have OSPF? Will OSPF die one day when SDN becomes more popular? That's the question. I close the poll. And the correct answer, at least the majority answer, which is probably the correct answer, is C. Of course, you still need a mechanism for the SDN controller to talk to the routers. So for that, you need somehow to be able to have communication everywhere. So if this is routers, you need a routing protocol, which may be OSPF or RIP or another one. If it's bridges, you need the spanning tree protocol with forwarding and learning to be able to talk to bridges that are not directly connected to the controller. In the lab, we use Mininet, and in Mininet, for most of the lab, we're in Mininet. Parts of the lab are also in the real physical world, but the part of the lab that's in Mininet hides this problem. In Mininet, we have a virtual environment with 4 routers, and of course, everything is virtual, so the central controller can directly talk to the routers by a magical mechanism that does not exist in reality. So in the lab, we may have a tendency to forget that we have this chicken and egg problem. In a real network, we will have it. So keep that in mind. Voilà, that's the tentative conclusion for this part on OSPF. But I will jump because I will add a little bonus part that is not on the slides, but will be in the version I will post later today. Let's talk a bit about what a protocol like OSPF is doing and about shortest path routing. Does a routing protocol maximize network utility? That's the question. We've seen it's better to have OSPF than having a spanning tree because we use all the links, but are we doing the optimal? Let me close the poll. We might be tempted to say yes, because it minimizes the cost to destination. Of course, it has nothing to do with TCP. So the only possible answer is perhaps C. Why is it? Well, first, it's not a well-posed question. We don't know what is the best in a network. So we need to give a metric that will say what is the best of a network. That will be the topic of next week. So we'll say, what does it mean to have maximum efficiency? But here we can see an example where whatever the metric, clearly shortest path routing will not be optimal. Assume I have this network and there is a flash crowd going from things connected to B towards services that are connected to E. So most of the traffic is going this way. If you do shortest path routing, then all traffic will go from B to E, right? So and the rest of the network will not be used. So assume the internetwork, the links are the bottleneck here. So I have, for example, 1 gigabit per second here, but the throughput of E is 10 gigabit per second, and the input to B is also 10 gigabit per second. Then I'm offering 1 gigabit per second for this entire traffic. Whereas if I had a smarter way of doing things, I could offer 3 gigabit per second. If there is negligible traffic on the rest of the network, I should diversify the route, have 1/3 of the traffic go here, 1/3 here, and 1/3 there. Right? This would be the optimal in this very simple form. Whatever your metric, probably, this is what you should do. Right? And shortest path routing will never do it, except if you manage to give the same costs to the 3 paths here. Right? So you can manipulate shortest path routing in order to have equal costs in this case here. This is one direction that is used by some. So the idea is to use dynamic link metrics. Instead of having static link metrics that depend on the capacity of every link, you want to match not just the capacity, but also the traffic situation. So the idea is to monitor what happens on a link. The higher the load on a link, the higher its cost. So this is used by some routing protocol like EIGRP that I'll discuss a bit again later. But we can imagine, for example, in OSPF that we monitor the link on the traffic utilization on every link. Assume, to simplify, all links are the same capacity, 1 gigabit per second. You can monitor how many packets per second are flowing on every link. And then you take some function that is inverse of 1 over the utilization that evolves in the reverse order. So the higher the utilization, the higher the so in the direct order, the higher the utilization, the higher the costs. For example, some functions could have an asymptote. When the utilization reaches 100%, then the cost reaches a very high value, right, which is reflecting the queuing behavior of everything. You could do this, and that would solve the problem here. Here, if we do this, then the cost on this link, then we'll see this link will be very largely utilized compared to the others. The others are quasi-zero, this one quasi-100%. So the cost of this link will be huge, will be the maximum value, 1 million, say, whereas the cost of those links is 1. So by doing that, the traffic will find, the OSPF will find shortest paths that are better here. So the traffic will go on these others, which will modify the costs. And at the end, we will find an equilibrium where there will be 3 equal cost paths, because if we diverge from that, the shortest path will be modified and traffic will move. So that's the idea. Now, what we'd like to see is that this apparently brilliant idea is not necessarily so brilliant because of something that is called Brace paradox. So Brace paradox is an instance of what occurs when everybody takes a local decision. So you have a problem. Here you see, for example, this link is very largely utilized. If I give to users or to the routing protocol the information that this path is better because there's less traffic on it, then that seems like a good idea. That's what Google Maps does with us. When we want to go from here to Geneva, we see if the road is red, we'll take the route cantonale instead of the autoroute, and because the autoroute is red here. If we do this, is it globally optimal? It's optimal for me, but if everybody does it, what is the resulting equilibrium? And then we will see that there is a paradox called Brace paradox that I'm illustrating on an example here. So Brace paradox has been found by Mr. Brace, who was studying traffic in cities, but since then the same paradox has been shown to happen also in computer networks. So the first topic that we have seen a minute ago is called the war-drop equilibrium. So assume I have a network and flows have some information of the delay, or the routers have costs that reflect the delay, the queuing delay, and the shortest path routes are the routes where the queuing delay is the minimum, right? Or let's say the queuing plus transmission delay. For example, here, assume my network is a lot of traffic going from the left to the right. I have different links. I have thin links that have little throughput, and I have thick links that have large throughput. And I have short links that have small latency, small propagation and transmission time, and the long links that have longer latencies here. Let's assume I have such a network here. Then what we have seen is that if we have dynamic routing, where the costs are updated to reflect the utilization of the link, then there should intuitively be an equilibrium. This equilibrium has a name. It's called a ward-drop equilibrium. The equilibrium is when the metric that we use is the same on both paths, because if it would not be the same, the shortest path would be this one, for example. It would attract more traffic here, which would also make its cost larger. So it's possible if eventually the thing must balance, because if they don't balance, one of the links will attract more traffic and will increase. Sorry, for this network, here I'm giving the delay on every link. So I have 6 gigabits per second on the left that want to go to the right. I have a first link that has a delay of 2 milliseconds plus 10 times the amount of traffic that is going here, right, in gigabits per second. So if all traffic goes this way, the delay on the first link will be 2 plus 10 times 6, that will be 62 here, plus here 48 plus 6. That will be the delay here. And similarly with exactly the same numbers here. Which one is a ward-drop equilibrium for this network? How will the traffic be split at equilibrium? I close the poll. Well, the only answer that makes sense, at least given the few seconds I give you to study this, is the symmetric answer. I mean, the delay characteristics of the two paths are the same. So intuitively, the symmetric answer should be the good one. It's not excluded that those two would have the same, but by doing the computation, you find that each of the two has a path that has a larger delay than the other. So in this symmetric case, there should be 50% of the traffic on both. Here. Now let's assume I want to improve this network and I add a link in the middle. Right. The previous situation is not a ward-drop equilibrium. In the previous situation, I had 50% of the traffic here, 50% there. But now what happens? All of a sudden there is this link which has a very small, is not used at all. I just opened it. So it has 0 or very, very little delay here. And the delay here is small, so the traffic that is here will see a new opportunity. Part of this traffic that was going here will go there. So the new ward-drop equilibrium will subtract some of the traffic that was here that will go there. Now this will reduce the delay on this part. I'll take 30 seconds on your break. This will reduce the delay on this path, so that will reduce the total delay for people who go left. So Google Maps will tell you by going left it's better. So there will be more traffic going here. If we do the computation of the end-to-end delay, we will find that in the new equilibrium that arises, the average delay for everyone will be 92 milliseconds instead of 83 before. Right? So opening a new link and having everybody following the shortest path routes gives to everyone a routing delay that is less than before. So adding capacity made things worse. Well, I will let you meditate about that, and perhaps we'll come back to this a bit later when we talk about routing again. See you tomorrow.